Greetings and welcome to the Chemistry 150% Potassium Chlorate in a Mixture lab. This is a fun lab. Wear your safety goggles. You're going to need them. We'll also see how chemists can figure out the percentage of an active ingredient when there's other not as exciting components in your mixture. So let's see what this lab has to offer. In the percent potassium chlorate in a mixture lab, the goal was we want to see how much potassium chlorate is in your mixture. And potassium chlorate, KClO3, all right? And KClO3 is a pretty active compound. It's used in things like fireworks and certain types of gunpowders, as I understand. But anyway, what happens is the KClO3, which starts pure, it is reactive and it does decay a little bit over time. So if you've had a potassium chlorate sample in your garage for a while, probably it's decomposed. And what it decomposes into, as we're going to see, is potassium chloride. So there's a chlorate, which is potassium chlorate, KClO3, and potassium chloride, KCl. And the goal is to find the percent of potassium chlorate in the mixture. The potassium chloride is not as exciting as the potassium chlorate. And what's worse is that KClO3 and KCl both are white solids. So just looking at the solid, you can't really tell if your sample is pure, if it's impure, how impure, like just a little bit or a lot. So this is a technique that scientists use sometimes to see how pure your potassium chlorate sample is. And again, potassium chlorate is what we're after because it's more exciting, more reactive than potassium chloride. Here's the overall balance reaction for what's happening. Potassium chlorate breaks down to potassium chloride and oxygen. And because oxygen is a diatomic, we're going to write it as O2, but the chlorate has 3 oxygens in it. So we're going to add stoichiometries of 2 and 2 to both of the potassium pieces there, while the oxygen gets a 3. Potassium chlorate breaks down to potassium chloride, but potassium chloride itself just sits there. It's a very stable and inert compound, not very exciting, all right? But the KClO3 will break down. It's going to break down into more KCl, and oxygen gas is going to come off too. It actually is going to like bubble a little bit. It's pretty sweet. So what we would do in this lab is we would use a Bunsen burner, which is this thing right here connected to a gas outlet, and up on the top we would have a ring clamp, which is that kind of circle thing right there. A triangle sits in the middle of it, and a crucible, which is this thing right here. A crucible would hold our sample, and the heat, when it's applied to potassium chlorate, makes it break down into potassium chloride and oxygen gas. As the oxygen gas is released, a lot of the mass is going to go away. Oxygen, like all gases, goes into the atmosphere, all right? And this only happens when you add a lot of heat to it. So as we break this down, it's the potassium chlorate which reacts. The potassium chloride just sits there and doesn't do anything. Now, it doesn't state it on this slide, but we're also going to use a catalyst, which is MnO2, manganese 4 oxide. The MnO2 just makes this reaction occur a little faster than it would have done normally. So all these things together, we'll be able to use this to figure out how pure our original sample was. Once you heat up the sample, again, it's the potassium chlorate which breaks down into the KCl and oxygen. But the oxygen, because it's a gas, it's going to look like we've lost mass, like before heating and after heating. After heating will be less. And we can record on a balance how many grams of oxygen have been left. And this is pretty cool. This is stoichiometry, the measure of amounts going in and coming out kind of thing. If you turn the grams of oxygen lost, and it's alpha here, it's a small number, usually like 0.5 or something. You can turn the grams of oxygen into moles, which is this part right here. And grams can be turned into moles using the molar mass. That's what beta is. So on the periodic table, oxygen is about 16 grams per mole. O2 would be twice that, or about 32 grams per mole. So you'd put 32 there in for beta, and that would turn your grams of oxygen into moles of oxygen lost. Then we've got this 2-3 ratio right here. And this comes from the fact that for every 3 moles of O2 that were lost, you had to have 2 moles of potassium chlorate in the original mixture. So we're turning moles of oxygen lost into moles of KClO3 in our original mixture using the stoichiometry of this balanced equation. Having a balanced equation, super cool in chemistry. You can do all kinds of things like that. So you can see here by the units that the grams of oxygen are going to cancel, the moles of oxygen will cancel, and at this point we would have the moles of potassium chlorate in the original mixture. But we want to turn this back into grams of potassium chlorate. So this little delta sign here, that's nothing more than the grams of potassium chlorate. Excuse me, start again. This lambda is the grams potassium chlorate. This is the molar mass. Sorry about that. This is the grams per mole of KClO3. So you're turning moles of KClO3 into grams of KClO3. Delta here is going to be a number. It's the molar mass. It's a number larger than 100, and I want you to calculate it. It shouldn't be too difficult. On the periodic table, look up a K, a Cl, and 3 O's. Add those numbers together. Whatever that number is, that's going to go in delta. And then this thing, the lambda here, that's what you're trying to solve for. You want to get the grams of the potassium chlorate in the original mixture. Most of the time, the lambda, this number you're solving for, it's going to be a number that's about a gram. It's not going to be a big number, sometimes 0.5 grams even. It depends on how much potassium chlorate you had in your original sample. Finally, you can use that lambda from the last thing, the grams of the pure KClO3 in your sample, and that's going to go right there. And if you measured the grams of the sample that you started with, which you should have as the good chemist, that's going to go on the bottom. So grams of the good stuff divided by grams of everything, or grams that you calculate of KClO3 divided by grams of the sample you started with times 100%, that is the percent KClO3. Percentages are almost always numbers less than 100 but greater than 0, as you can probably imagine. In this lab, they do have quite a big range. It's usually it's larger than 10% but smaller than 90%. Some of them can get close to 90% though, so just go with the flow. On this lab, make sure that you watch your significant figures, all right? There's going to be a couple of things in there to watch for. This is good chemistry measurement here, so we've got to do it. But otherwise, it's pretty chill. So the goal of this lab, tell me the percent of KClO3 in the mixture. And all those steps we just went through should be good to go. All right, at this point, I think it's time to watch a video that shows the actual process. Again, if you have questions on any of this stuff, please let me know. Good luck on the lab.